The one with the chart thing.
Yep. Okay, so before I give you more notes up here, I'm going to read all the answers again to this to make sure you got it. So just follow with me here. Number 1, activation energy of the forward without a catalyst. I'll say that again. Number 1, I know the line is small. Activation energy of the forward reaction without a catalyst. If you wrote just activation energy, that's good enough, but specifically it's the forward reaction and without a catalyst. Number 2, activated complex. Number 2 is activated complex. Number 3, delta H or heat of reaction. Either one. 4, energy of reactants. 5, energy of products. 6, that is the activation energy of the forward reaction with a catalyst. So if you wrote activation energy with a catalyst, that's good enough. Activation energy with a catalyst for number 6. Number 7, activation energy of the reverse reaction with a catalyst. Number 7, activation energy of the reverse reaction with a catalyst. And then number 8, activation energy of the reverse without a catalyst. Number 8, activation energy of the reverse without a catalyst. So again, that's kind of just notes, a reference sheet for you to help on homework. Anytime you have something you're working on, you don't remember something, that's what it's for. It's just notes, okay? So keep that with your stuff. Okay, you're copying both of these down. Table I should be open. And I'm going to add some things here. I'm going to put an arrow to the top of that peak. I'm going to label it number 1. So you're going to do the same thing. I'm going to put an X on the top of the peak, and I'm labeling that number 2. Do the same thing. Now I'm going to label in between the, well here, let me back up. This line over here, let's label P. What's that P stand for? Products. R in the beginning, put an R right here. I want to make this real clear before I go any further. The beginning of these diagrams, that's your reactant. The end of them, over on the right, that's your product. And that's what these diagrams show. I don't think I explained that well enough yet. These diagrams show energy changes during a chemical reaction. I showed you one yesterday, how it reacted faster. I'll get to that in a little bit. I'll show you another example of a reaction today. All reactions have these diagrams. That's what this charts. Energy changes in a reaction. So reactants here, products here, arrow 1, X2. We're going to put another arrow right here between the P and the R. That's our delta H. Oops. Let's keep it consistent. That is delta H, but let's label number 3. And then over on the side, I'm going to write down what they are. Just makes it a little neater, I think, instead of writing all the words and stuff on it, all the phrases. Over on the right side, I'm not going to label all the same things. I'm just going to label number 3. So I'm going to keep number 3 consistent, but 1 and 2 I'm not going to label. It's redundant. Number 1 is the same on both graphs. Number 2 is the same. In other words, the same location. It might be a different value, but it's the same location, so I don't want to label it twice. Make sure you get all that down before we start taking some notes here. We started defining these things yesterday, we didn't finish it. All right, looks like we're good to go. All right, number 1. What is number 1? Evan, what's arrow number 1 tell us? What is that interval called? You can look at the sheet you just had out if you want. What's that called? From the reactants to the top of the peak. What's that called? Yeah, activation energy. So number 1 is activation energy. And that's without a catalyst. So I'm just going to put without catalyst. Yeah, that's activation without a catalyst. Bree, what is activation energy? Remember from yesterday what I said?
The amount of energy it takes for a reaction.
Good. It's the energy needed to to start a reaction. And the way Bree worded it was for a reaction to occur. Same thing. In order for a reaction to occur or start, it needs a certain amount of energy. That's what activation energy means. Activation means start. So, that's the definition. If you are standing here on the R and you have to get to the top of the peak is where things collide and react. To go from here to here, it's got to gain energy. That's what this is. It's the energy to get to the top. That's activation energy. Number 2, activated complex. I just called it out there. Activated complex. Some books will call this the transition state. Transition state. Because it's between reactants and products. What happens at the top, Jake's going to tell us. Jake, give me one thing needed for an effective collision. Sufficient energy, good. So if we get enough energy to get to the top, that's half the battle. We have sufficient energy. Taylor, what's the other part of that? To have an effective collision. We need enough energy so they hit each other hard enough. And? Orientation, good. So at the top, that's where those two things happen. Activated complex, that's where the effective collisions occur. Effective collisions happen. Okay? Right at the top. If it has enough energy, if it has the right orientation, guess what happens? So we're right at the top, particles are colliding. If this does occur, what happens? So look up here. You start out as reactants, just separate, not doing anything. If they gain enough energy to get up there, that means they can start reacting. Then they start colliding. If both of those things happen, it's called effective. So if you have an effective collision right here, what happens? Yeah, products are formed. Guess what happens if you don't have effective collisions? So you're standing at the top.
If you don't have effective,
there's
going to be no reaction.
So what you're here, what happens?
You're going to stay there.
Nope.
No.
You fall back to the reactants. So this is the transition state because that determines on what happens. If this occurs, you make products. If it doesn't, it falls back to the reactant. Think of it, you can think of it as kind of like rolling a ball up the hill. If you roll the ball and it just gets to the top, I mean, I suppose it could stay there. But let's say it doesn't. It either gets enough energy to go or it comes back to you. Think of it that way. Maybe that'll help. So if it works, it'll continue to go. If it doesn't work, no effective, then it comes back down. So that's the activated complex. All right. Number 3, we're going to define next here. I'm just going to erase this. Number 3, that's our delta H. So number 3, that's our heat of reaction, and that's delta H. That's delta H, number 3. Now, Blake, what's delta stand for? Okay, that's fair. Sarah? Delta? Chuck? Change, yes. Delta means change or difference. So, number 3 is delta H. Delta H, feel free to label that. What is it the change of, Isla? It's delta H. Delta means change. What do you think H means? Heat. So change. Use a different word instead of heat. So this segment here is the change in heat. This segment is the change in heat. But use another word instead of heat. Energy, very good. So delta H tells us the change in energy between reactants and products. I said that backwards. Reactants and products. Here, it's reactants and products. Notice that these are kind of flipped, sort of. Here, the reactants are low, products are high. Here, the reactants are high, products are low. Let's label that R and P. So, what does the heat of reaction tell us? The change in energy between products and reactants. Oops. Like Isla said. Between products and reactants. This tells us if it's endothermic or exothermic. Endo or exo is determined based on that. Go to table I for me, once you're done with that. Actually, you know, hold on. Let me write one more thing. The way we get the delta H equals the heat of products minus heat of reactants. That's how we get the delta H, like an actual number for it. Heat of products minus heat of reactants. So I labeled on both graphs the energy of reactants and energy of product. One of them's 30, one of them's 60. You guys are all big boys and girls. You can do simple subtraction. Calculate the delta H for this one on the right. Calculate the delta H for this one on the left. You can write it down or do it in your head. And then I'll call on somebody to tell us. So to find the delta H, it's the heat of the products minus heat of the reactants. So calculate the delta H for here. Calculate the delta H for here. Go ahead. I'll give you 1 minute and I'll call on somebody. You know, it shouldn't take a minute. Heat of products minus heat of reactants. I labeled both for you. All you have to do is subtract. Yeah, I'm too antsy. I'm not waiting a minute. That would take too long. Okay, there's 40 seconds. All right, who can give me the delta H for this one right here? Edwin, sounds good. Products minus reactants. Heat and energy are the same thing. So I labeled your products, I labeled your reactants.
So it's -30.
Negative 30, how'd you get that? Very good. 30 minus 60, everybody underneath here, right? Delta H equals 30 minus 60 equals negative 30 kilojoules. Very good. Negative 30 kilojoules. Products, 30. Reactants, 60 kilojoules. Subtract 30 minus 60. Products minus reactants, negative 30. Good. All right, over here. Ryan, what's the delta H?
30.
How'd you get it?
I don't know. Don't you minus 30 minus 60? Or is it 60 minus 30?
Okay. Focus now.
Yeah.
Products minus
Yeah.
reactants. That's how we get delta H. Products
Okay.
minus reactants. So 30 minus 60, that's where this comes from.
So it's negative 30.
So over here,
No, it's positive 30.
what do I subtract? Tell me what to
60 minus 30.
Very good. 60 minus 30. And the reason he figured that out is because the products are labeled 60 kilojoules, reactants labeled 30. 60 minus 30 equals positive 30 kilojoules.
You made me second guess myself.
Good. All right. Go to table I. Use table I to help answer the following question, and then Jenny's going to tell us. Which graph up here, left or right, is exothermic? Which graph, left or right, is endothermic? The way you figure it out is you subtract your products minus reactants in terms of heat. You get a value for delta H. Table I gives you a little hint as to which one is endo, which one's exo, in case you forget. So we'll give Jenny another little bit here, but the rest of you should be figuring this out in your head. Based on the value of delta H, you should be able to tell me from something we learned early in the year, which one is exo, which one is endo. If you forget, that's why we're doing it right now. So that's okay. All right, Jenny, what do you think?
The first one is exothermic, and then the other one is endothermic.
Very good. This is exothermic. Good job. This is endothermic. Jenny, how do you know?
Because that first one has a negative 30 for delta H, and the other one is positive.
Good job. Negative means exothermic. Positive delta H means endo. Look at the very bottom of table I. It says minus sign indicates exothermic. You don't have to memorize it. It's right there. Okay? But you should remember that anyway. Okay. Devin, what does exothermic mean? Releases. So what's endothermic mean? Absorb. So everybody look up here. Most of you are already, but forget the number here for a second. Just look at the graph. If the y-axis is energy, potential energy, I hope you can all figure out this is endothermic just by looking at the graph. Because your reactants are low, products are high. That means throughout this reaction, it gained energy. So it has more at the end than it did in the beginning. That's gaining. That's endo. Over here, you have less at the end, more in the beginning. So as this reacted, it got rid of energy. That's exo, because your products are lower and your reactants are higher. So I hope you can look at it and figure it out, because sometimes on the regents or a quiz or test, they're not going to give you numbers. They're just going to give you a graph without actual numbers. So you have to be able to pick which one's exo and endo. So I guess I could explain that in terms of that's kind of like common sense, I think. This is a little bit harder where you have to figure out the numbers. So hopefully you guys can look at it and figure it out. That was the goal for today, besides defining this stuff, is learning this. Exo, endo, and how to figure it out. Okay? So 2 ways. With the numbers, if you don't have the numbers, look at the graph, see which one makes sense to gaining or losing. Questions on that? Trying to be as clear as I can here. Go ahead. Should do theater. No questions. We're good to go. Okay, now, table I. Look at the very first reaction on table I. Let's just make sure we understand. Look at the very first reaction on table I. Which graph, left or right, could we use to represent the first reaction? Forget all the numbers. Let's say there were no numbers. Which graph? The first one here on the left. So we'll say left. Left or right? Which one could we use to represent that very first reaction on table I? Shelby Johnson. Why? Is the reaction on table I, the first one, exothermic? How do you know? Negative sign. So the way the regents will ask this, according to table I, given the following equation, which of the following potential energy diagrams are correct? They'll give you 4 of these. They'll give you the reaction from table I. You go look it up on table I. Let's say it's the first reaction. You look and see, okay, delta H is negative. What does that mean? Exothermic. Okay, which one's exothermic? This one. That's the answer. That's how we use table I and this at the same time. That's how, they could ask you questions. All right? So we're good with that. All right. Good. Still got some time. All right. I'm going to erase all this. I'm going to sketch another one. Don't put it up. Don't put it in your notes yet. We're going to take notes on catalysis, which is catalyst, and then we'll do a demo. All right. Here we go. You can, but I'm going to be going fast, so hustle up. All right. So in our notes, we're writing catalysts. And then over to the side, we're going to have another diagram. I always tend to draw exothermic. I don't know why. Just a personal preference, I guess. Exothermic are more fun. Usually explosions, fire. What's a catalyst? Let's see. Who have I not talked to today? Shelby. I don't think I called on you yet, have I? What's a catalyst? Anything that speeds up a reaction. Good. A substance that speeds up a reaction. Very good. Makes the reaction happen faster. Increases the reaction rate. That's like the fancy way to say it, right? Increases the reaction rate, meaning it works faster. Okay? Guys ever hear of a catalytic converter? Where are those?
All over the place. They're in Cadillacs, obviously.
Catalytic converter. Anybody know what it is? What it does? How?
We're going to use context clues. It's a converter. It converts things.
Well, catalytic means catalyst, right? So it helps something react faster.
So it helps.
Who's heard of that?
It just gets rid of the emissions in the car.
Okay, it gets rid of emissions in the car. You didn't raise your hand though, so it has to do with a car, right? Okay? Yeah, if there's a special chemical coating inside there that helps with the emissions, but it helps work faster. Catalytic, right? Trying to give you an example. Say it again.
Makes your car quieter too.
Yeah, it makes the car quieter too. So, substance that speeds up a reaction, that's a catalyst. So, I'm going to show you a very good example of a catalyst today. How does it do it though? So, how does it do it? Draw this if you didn't already. Get another one in your notes. This is a reaction without a catalyst. If you want to show a catalyst, what do we do? This kind of gives you a hint. What do we do? How do we show a catalyst on that? It's right in front of you. If you're looking at this, which one here shows, which one is the catalyst? The lower one. So you draw another bump or a hill, but you do it with a dotted line. So do this. Start here, follow the same curve to the best you can, and end it there. Do not cross the line or finish under the line. It has to be exactly where the reactants start, exactly where the products end. Don't let that dotted line move. Okay, it has to start and end at the same spot as the other reaction. The middle part is where it's lower. Okay, that's how you draw a catalyst. What does it do? It provides an alternate pathway. An alternate pathway for a reaction. That's what a catalyst does. How does it do it? Well, let's say somebody's standing here. Maybe they're smiling. Maybe they have long hair. This is going to be Ryan if he doesn't get a haircut.
Yeah, I gotta go on.
Okay?
Some, I don't know, stuff in your hair there, little bow ties at the end there.
Okay, so Ryan with long hair wants to climb the mountain. Which way is easier, the dotted line or the solid line?
I was just gonna dig a hole right through it.
We did this yesterday. Which one's quicker? Dotted, right? So if he goes here, he'll get to the top quicker, and then he's down, he makes products. If he goes up here, it'll take a little bit more time. It'll still work, but it's slower. Don't write all those lines, it's confusing. But the dotted line is a quicker alternate path. So what does it actually do? Who remembers, what's this arrow right here called? From the reactants to the top of the peak, what's that called? Activation energy. So what does a catalyst do? Let me erase all this and draw it again. All right, so here's the catalyst underneath here. So what does a catalyst do? What does it do? Very good, Xavier. Lowers the activation energy. Lowers the activation energy. Good job. So a reaction occurs faster with a catalyst because it lowers the activation energy. It takes less energy to start. Yesterday, I did not show you a catalyst. What did I do? I had the two reactions there. One on the right was what? When I poured the liquid, it was what? Hotter. Why did it react faster? Because there's more energy. It bumped up that activation. It gave the reacting particles energy to get to the top faster. That's different than what a catalyst does. So let me explain that again. If you heat something up, you're bringing the reactants up. If you add a catalyst, it's bringing the bump down. That's what a catalyst does. It lowers the activation energy. So you don't have to heat it up. Maybe it'll react faster without heat because you're lowering that activation energy. These three things are the most important thing to remember about a catalyst. There's a couple more things we got to add, but I want to make sure we have time to do the demo and talk about it a little bit. We have a little more time in period 2. I was rushing at the end of period 2. But regents really like to ask questions about a catalyst, what it does and how it works. Okay, lowers that activation energy. So let's go back, let's do the demo, and that'll probably be it. We'll be pretty close to the end here.